July 23, 1944. The hedgerows of Normandy, France. Staff Sergeant Curtis G. Collin, Jr., of the 2nd Armored Division, sat in the dirt beside his disabled Sherman tank, staring at a problem that had killed more American tankers in 3 weeks than German anti-tank guns had managed in 3 months. The tank wasn't damaged by enemy fire. It was stuck, immobilized, helpless, buried nose down in an ancient Norman hedgerow that German defenders used as ready-made fortifications. Around him, across the Norman countryside, hundreds of American tanks sat similarly trapped or destroyed, victims not of superior German armor or tactics, but of geography that American planners had catastrophically underestimated. The hedgerows, called bocage by the French, were earth berms 4 to 8 feet high, topped with dense vegetation, roots tangled over centuries into barriers harder than concrete. They crisscrossed Normandy every 100 yards, turning the entire region into a massive defensive maze. Standard doctrine for crossing these barriers required tanks to climb them head-on, but the Sherman's center of gravity was too far forward. As the tank climbed, its nose would rise, exposing the thin belly armor to German guns. At the moment of maximum vulnerability, often the tank would lose traction, the tracks spinning uselessly, while the tank balanced on the hedgerow peak like a seesaw. German anti-tank teams called it the American present, the gift of an immobilized Sherman silhouetted against the sky, belly armor exposed, crew trapped inside. In 3 weeks of hedgerow fighting, the Allied advance had slowed from miles per day to yards per hour. Casualties were mounting. Entire battalions were pinned down. General Omar Bradley's staff estimated at the current rate it would take until Christmas to break out of Normandy. The war that was supposed to end by autumn 1944 was in danger of dragging into 1945 or beyond. Cullen, a 29-year-old cab driver from Cranford, New Jersey, before the war, had no formal engineering training. He had a high school education and 3 years of experience maintaining taxis. But as he sat in the Norman mud that July afternoon, watching another Sherman expose its belly and die, he had an idea. An idea so simple it seemed ridiculous. An idea that would cost approximately $5 in scrap metal to implement. An idea that would save thousands of American lives and fundamentally alter the Normandy campaign. The transformation would begin, not in a laboratory or engineering department, but in a field maintenance area with cutting torches, welding equipment, and steel salvaged from German beach obstacles. Within 2 weeks, Collins' improvisation would be standard equipment on thousands of American tanks. Within a month, it would help break the deadlock that threatened to stall the liberation of France. The innovation would eventually bear his name and earn him a Legion of Merit medal, but the recognition would come decades after the war, when historians finally understood what one mechanic's $5 fix had actually accomplished. The Normandy Nightmare. The D-Day landings on June 6, 1944, had succeeded beyond anyone's expectations. Allied forces had secured the beaches, established a beachhead, and begun pushing inland. Intelligence reports had warned of difficult terrain, but nothing prepared the tankers for the reality of the Norman bocage. The hedgerows dated back to Roman times. Perhaps earlier, Norman farmers had built earth berms to mark property boundaries and prevent soil erosion. Over centuries, vegetation had grown atop these berms, roots penetrating deep into the earth, creating barriers that were part geology, part botany, entirely impassable. The typical hedgerow was 4 to 6 feet of packed earth, topped with another 2 to 4 feet of tangled brush, trees, and thorny undergrowth. The root systems extended 8 to 10 feet deep. American pre-invasion intelligence had identified the hedgerows, but catastrophically underestimated their impact. Aerial reconnaissance photos showed them as simple field boundaries. The intelligence assessment described them as earth and hedge fences, approximately 3 to 4 feet high, presenting minor obstacles to armored vehicles. This assessment would prove to be one of the war's most costly intelligence failures. The reality facing tankers in early July was nightmarish. The hedgerows created thousands of small enclosed fields, each one a potential kill zone. German defenders positioned machine guns, mortars, and anti-tank weapons in the corners, knowing exactly where American tanks would attempt to cross. They had months to prepare. Every field was pre-sighted for artillery. Every hedgerow breakthrough point was covered by interlocking fire. The Sherman tank, America's primary armored vehicle, weighed approximately 33 tons and was powered by a Wright Continental R975 radial engine, producing 400 horsepower. It was reliable, easy to maintain, and produced in staggering quantities. By July 1944, American factories had built over 40,000 Shermans, but the Sherman had never been designed for hedgerow country. When a Sherman approached a hedgerow at the required angle for climbing, the tank's nose would rise as the front tracks encountered the earth berm. As the tank climbed, its center of gravity shifted backward. At approximately 30 to 40 degrees of climb angle, the belly of the tank, protected only by 1/2 inch of armor, compared to 3 inches on the front glacis, was completely exposed. German anti-tank teams armed with Panzerfaust rockets, or Panzerschreck launchers, would wait for this moment. A single hit to the belly armor would penetrate to the engine compartment or ammunition storage, typically causing catastrophic fire. American tankers called it brewing up. German soldiers called it Tommy Cookers. The alternative to climbing the hedgerows was to find gaps, but these were few and always covered by German weapons. Engineers could blow gaps using explosives, but this was slow, dangerous, and announced to every German within earshot exactly where the attack would come. Bulldozer tanks could push through, but the army had only a handful of these specialized vehicles. By mid-July, the 2nd Armored Division had been fighting in hedgerow country for 5 weeks. Casualty rates were approaching 50% in some tank battalions. Tank losses exceeded replacement rates. Morale was deteriorating. Veterans who had survived North Africa and Sicily were being killed in anonymous Norman fields, whose names wouldn't even appear on maps. Staff Sergeant Curtis Cullen's company had lost 4 tanks in 2 days to hedgerow ambushes. He had watched friends die in burning Shermans, trapped by hatches jammed shut from the violence of ammunition explosions. He had seen tank commanders shot by snipers as they tried to spot German positions while navigating hedgerow crossings. He had personally survived 2 knockouts, once bailing out seconds before his tank exploded, once staying with a tank that burned for 4 hours before it could be recovered. The frustration among tankers was reaching critical levels. They were dying not because German tanks were better, though the Panthers and Tigers certainly outclassed the Sherman in armor and firepower. They were dying because of terrain, because of geography, because American doctrine and equipment hadn't accounted for fighting in a landscape that turned every 100-yard advance into a separate battle. The $5 solution, den Mordibeying Bedingteven Beitir. On July 23, during a maintenance stand-down after a particularly costly week of operations, Cullen walked through a field of German beach obstacles being salvaged for scrap metal. The obstacles, nicknamed Rommel's asparagus, were steel rails driven into the beach sand to impale landing craft. Allied engineers had blown them up or pulled them out, leaving thousands of tons of scrap metal scattered along the Norman coast. Cullen picked up a piece of steel rail, approximately 3 inches by 3 inches in cross-section, 6 feet long, weighing perhaps 40 pounds. He hefted it, examined it, and had his breakthrough insight. If these steel rails were welded to the front of a Sherman in a specific configuration, they could act as teeth or tusks, cutting into the hedgerow base before the tank's nose began to rise. Instead of climbing over the hedgerow, the tank could theoretically plow through it. The concept was mechanically simple. 4 steel prongs welded to the tank's lower front plate would dig into the earth berm as the tank advanced. As the tank pushed forward, the prongs would cut through roots and soil, creating a passage at ground level rather than forcing the tank to climb over the obstacle. The tank would remain horizontal throughout the crossing, never exposing its vulnerable belly armor. Cullen sketched his idea on a piece of paper torn from a ration carton. He showed it to his tank commander, Lieutenant Dan Bailey, who was skeptical but willing to test it. "It'll probably tear the prongs right off," Bailey said. "But hell, it can't be worse than what we're doing now." The next morning, Cullen and 3 other mechanics from the company maintenance section took cutting torches and welding equipment to the scrap pile. They selected 4 pieces of steel rail, each approximately 6 feet long. Using a cutting torch, they cut angles on one end of each prong to create sharp points. The other end they cut flat for welding to the tank hull. The welding took most of a day. The prongs had to be positioned precisely, angled slightly downward, spaced evenly across the front of the tank. The steel was heavy, and the welding was done in field conditions, without proper fixtures or jigs. Cullen and his team used wooden blocks and rope to hold the prongs in position while they welded. The welds were rough, functional rather than pretty, but they held. The material cost was zero, all salvaged scrap. The labor was performed by tank crew using their own time. If the Army had requisitioned such a device through proper channels, accounting for design, testing, approval, manufacturing, and distribution, the cost would have been hundreds of dollars per tank, and taken months. Cullen's version cost maybe $5 in welding rod and cutting torch fuel. It took 1 day to build. The test came the next morning. Cullen's Sherman, now sporting 4 steel tusks protruding from its front, like some mechanical wild boar, approached a hedgerow that had stopped 3 previous tanks. Bailey, commanding from the turret, gave the order. Cullen, driving, shifted into low gear and advanced at walking speed. The steel prongs bit into the hedgerow base. The tank's engine note changed as the load increased. The prongs bent slightly but held. The tank pushed forward. Instead of climbing, it was cutting, plowing, boring through the centuries-old earth and roots. Clumps of soil and vegetation sprayed outward. The tank remained level, belly armor protected, moving forward steadily. 30 seconds after entering the hedgerow, the Sherman broke through into the adjacent field. The tank was undamaged. The prongs were bent but intact. The crew was ecstatic. For the first time since landing in Normandy, they had crossed a hedgerow without exposing themselves to suicidal vulnerability. If you're fascinated by how simple innovations can change the course of history, make sure to subscribe to our channel and hit the notification bell. These are the stories of ordinary people who achieved extraordinary things that shaped our world, proving the concept. Word of Collins' successful hedgerow crossing spread through the 2nd Armored Division within hours. Tankers who had been fighting hedgerows for 5 weeks knew immediately what this meant. Officers who understood tactics recognized the implications. If tanks could cross hedgerows without exposing their bellies, the entire tactical equation of hedgerow fighting would change. Captain James M. Burt, commanding Company B of the 66th Armored Regiment, was one of the first officers to recognize the innovation's potential. Burt, who would later earn the Medal of Honor for actions in Germany, had lost 8 tanks in hedgerow fighting in 10 days. He immediately ordered his maintenance section to fabricate similar devices for every tank in his company. The problem was materials. The German beach obstacles had been mostly salvaged and distributed. The maintenance sections needed more steel. The solution came from an unexpected source: destroyed German tanks. The Normandy battlefield was littered with knocked-out Panthers, Tigers, and Panzer IVs. Their armor plate, while too hard to cut easily with field equipment, had structural steel components, rails, braces, and frame members that could be salvaged. Over the next 3 days, maintenance crews from multiple battalions descended on the German wrecks like scavengers. They cut steel from engine decks, track guards, and hull structures. They salvaged leaf springs from suspensions. They took anything steel that could be cut, shaped, and welded. The Germans had unknowingly provided the material for the device that would help defeat them. By July 27th, 4 days after Cullen's initial test, approximately 30 tanks in the 2nd Armored Division had been fitted with the improvised hedgerow cutters. Field tests began immediately. Different designs were tried. Some tanks had 4 prongs, some 6. Some prongs were straight, some curved, some were welded in a horizontal line, others in a V configuration. The tests revealed optimal design parameters. 4 prongs worked better than 6 because they concentrated force more effectively. The prongs needed to be angled downward approximately 15 degrees to bite into the soil, rather than pushing it. Spacing of approximately 18 inches between prongs prevented the hedgerow from pushing up between them. Overall protrusion of 4 to 6 feet provided sufficient leverage without adding excessive weight. The devices also needed to be robust. Early versions sometimes broke welds or bent excessively. Reinforcement gussets were added. Heavier steel sections were used. By the end of July, the design had evolved through practical experience into a configuration that was both effective and durable. But effectiveness alone wasn't enough to gain official acceptance. The U.S. Army in 1944 operated on procedures, regulations, and chain of command. Sergeants didn't simply modify Army equipment, even in combat zones. Officially, the tanks were government property. Modifications required approval from Ordnance Department. Testing and evaluation required weeks or months at proving grounds. Field modifications violated regulations and could result in court-martial. The tankers didn't care. They were dying in hedgerows, and Cullen's device saved lives. Company commanders looked the other way. Battalion commanders tacitly approved. But regimental and division-level commanders faced a dilemma. They could see the device worked, but officially authorizing its use meant taking responsibility for an untested modification that violated regulations. Bradley's decision. The breakthrough came when General Omar Bradley, commanding 1st Army, visited the 2nd Armored Division on July 30th. Bradley was touring frontline units to assess the tactical situation. The hedgerow fighting had stalled his offensive. He needed solutions. During the visit, Captain Burt arranged a demonstration. 2 Shermans would attempt to cross the same hedgerow. The first tank would use conventional tactics. The second would be equipped with Cullen's device, which some tankers were already calling Cullen teeth or rhino horns. The first tank, using conventional technique, approached the hedgerow at 10 miles per hour. It began climbing. The nose rose. At approximately 35 degrees, the belly was completely exposed. The demonstration crew had placed a white panel on the ground in the German observation position to show where an anti-tank team would be positioned. From that position, the tank's vulnerable underbelly was perfectly silhouetted. After cresting the hedgerow, the tank bogged down momentarily, exactly when it would be most vulnerable to follow-up shots. Total crossing time, 43 seconds of maximum vulnerability. The second tank, Collins' modified Sherman, approached the same hedgerow at walking speed. The steel prongs bit into the earth. The tank remained level throughout the crossing. From the German observation position, the tank presented only its heavily armored front. The belly armor was never exposed. The tank broke through in 28 seconds and immediately had clear fields of fire. The tactical advantage was overwhelming. Bradley, who had commanded combat units in North Africa and Sicily before taking First Army command, understood immediately. This wasn't just an interesting field modification. This was a potential war winner. The device would allow armored forces to operate in hedgerow country with reasonable safety. It would restore mobility to armored operations. It would save lives. But Bradley also understood the institutional obstacles. The device was untested by official standards. It hadn't been evaluated by Ordnance Department. Using salvaged German steel might violate laws of war. The welding quality was inconsistent. Official approval would take months that the campaign couldn't afford. Bradley made one of the war's most important command decisions. He would bypass official channels completely. First Army would approve immediate field modification of all Sherman tanks under his command. Ordnance regulations would be waived. Materials would be sourced from any available supply. Every division would establish fabrication teams. The goal was to equip every Sherman in First Army, approximately 3,000 tanks, within 2 weeks. This decision was extraordinary. A theater commander was authorizing wholesale modification of major weapons systems based on a 3-day field trial of a device invented by a sergeant. No testing program, no engineering evaluation, no approval from Washington. Just a command decision that the device worked well enough and was needed immediately. Bradley's order went out on August 1st. Division and corps commanders received instructions to form fabrication teams, source materials, and begin immediately. The maintenance sections, normally responsible for repairs, became manufacturing centers. Welders worked around the clock. Steel was sourced from everywhere. German wrecks, beach obstacles, abandoned equipment, even rail lines in rail yards. Mass production in a war zone. The fabrication effort revealed American military logistics at their most impressive. Within 48 hours of Bradley's order, the First Army had established a coordinated production system across Normandy. The 2nd Armored Division, having the most experience, became the template. Their maintenance section documented the design specifications, prong dimensions, spacing, angles, reinforcement requirements, welding procedures. These specifications were distributed to other divisions via courier and radio. Each division established fabrication sites near their maintenance areas. The sites were organized like assembly lines. One team cut steel to length using cutting torches or saws. Another team shaped the prongs, cutting points, and mounting flanges. A third team positioned and welded the prongs to tanks. A fourth team inspected welds and reinforced any weak points. The limiting factor was welding capacity. Each device required approximately 4 hours of welding time. With multiple teams working simultaneously, a division maintenance section could equip 4 to 6 tanks daily. To meet Bradley's 2-week deadline for 3,000 tanks, the Army needed to equip approximately 200 tanks daily across all divisions. The solution came from unexpected sources. Combat engineer battalions had welding equipment for field fortification work. These engineers were redirected to tank modification. Ordnance companies, responsible for ammunition supply, also had welders. They joined the effort. Even Navy Seabees, construction battalions supporting beachhead operations, contributed welders. Material supply remained challenging. The initial plan to use salvaged German steel couldn't scale to thousands of tanks. The Army needed a steady supply of structural steel. The solution came from Omaha Beach, where the port facilities were being expanded. Construction crews building the artificial harbor had steel I-beams, railroad rails, and structural steel brought from England. Some of this material was diverted to tank modification. Additionally, damaged landing craft being scrapped provided steel plate and frame members. The logistics officers calculated they needed approximately 12 tons of steel daily to maintain production rates. They found 20. Quality control was improvised but effective. Each division assigned an officer, usually from Ordnance, to inspect completed modifications. The inspection focused on weld integrity and prong angles. Tanks that passed inspection received a white-painted X on the prongs. Tanks that failed were sent back for reinforcement. The rejection rate was approximately 10%, remarkably low for field welding under combat conditions. By August 10th, 9 days after Bradley's order, approximately 1,800 tanks had been modified. By August 15th, over 2,500 tanks carried the hedgerow cutting devices. The fabrication effort was succeeding beyond expectations. Operation Cobra unleashed. The strategic timing was perfect. Bradley had been planning a massive breakout operation called Operation Cobra, scheduled to begin July 25th. The operation had been delayed due to weather and logistical issues. The rescheduled date was August 1st, exactly when the hedgerow cutters were beginning to reach frontline units in significant numbers. Operation Cobra was designed as a sledgehammer blow. 3 infantry divisions would punch a hole in German lines following massive carpet bombing by heavy bombers. Then 3 armored divisions would pour through the gap and break out into the French countryside beyond the hedgerows. The plan required armored mobility. Without the hedgerow cutters, that mobility would have been severely constrained. The operation launched on August 1st. The initial assault by infantry and armor faced the expected German resistance, but tankers immediately noticed the difference. Hedgerows that previously would have stopped attacks cold were now penetrable. Tanks equipped with Cullen cutters plowed through hedgerows, maintaining momentum, keeping German defenders off balance. The tactical impact was immediate. German defensive doctrine assumed hedgerows would canalize attacks into predictable crossing points. Defenses were concentrated at these points, but tanks with cutters could cross almost anywhere. German defenders suddenly faced attacks from unexpected directions. Their carefully prepared positions were bypassed or flanked. Technical Sergeant Eugene Luciano, commanding a Sherman in the 3rd Armored Division, recorded in his diary, "The difference was night and day. Before the rhino horns, crossing a hedgerow meant saying your prayers and hoping for the best. With the horns, we just put our heads down and bulled through. We crossed 6 hedgerows in 1 hour. Before 6 hedgerows would have taken 6 days and cost half our tanks." By August 5th, American armored spearheads had broken through the German defensive crust and were operating in more open terrain beyond the densest hedgerow country. By August 10th, the breakout was accelerating. German defensive lines were collapsing. By August 25th, Paris was liberated. The Normandy campaign, stalled in hedgerows for weeks, had suddenly exploded into rapid advances. Military historians debate whether Operation Cobra would have succeeded without the hedgerow cutters. German forces were depleted and exhausted. The massive aerial bombardment was devastating. American numerical superiority was overwhelming, but historians universally agree that the hedgerow cutters significantly accelerated the breakout and reduced American casualties during the critical phase. If you're enjoying these incredible stories of innovation and determination in history, please take a moment to subscribe to our channel and hit the bell icon. Your support helps us continue bringing you these fascinating true stories. Recognition and evolution. Curtis Cullen himself almost missed Operation Cobra. On July 30th, the same day Bradley saw the demonstration, Cullen's tank was knocked out by a Panzerfaust during a reconnaissance mission. Cullen survived without injury, but spent 2 days evacuated for observation. He returned to his unit on August 2nd to find his improvised device being mass-produced and installed on thousands of tanks. His battalion commander, Lieutenant Colonel Hugh O'Farrell, recommended Cullen for the Silver Star for his innovation. The recommendation was upgraded to Legion of Merit at division level, but the award process moved slowly. Cullen wouldn't receive the medal until October 1944, and the citation didn't mention the hedgerow device specifically, referring instead to meritorious service in maintenance operations. More importantly to Cullen, his innovation was saving lives. He could see tanks in his battalion equipped with his device crossing hedgerows safely. He could see attacks succeeding that previously would have failed. He knew, with absolute certainty, that soldiers were going home to their families because of something he invented. The device evolved rapidly through August and September as more units gained experience. Several improvements emerged from field use. Some units added horizontal braces between prongs for extra strength. Others experimented with different prong angles for different soil conditions. A few units even motorized the prongs, allowing them to be raised and lowered, though this modification was rare due to complexity. The most significant evolution was standardization. By mid-August, the Ordnance Department had finally caught up with field developments. Engineers at Holabird Ordnance Depot in Maryland designed a standardized version of the device, incorporating lessons from field use. The official designation was Hedgerow Cutting Device, M1. Contracts were issued to manufacturers in the United States to produce them properly. But by the time factory-produced units began arriving in France in September, they were largely unnecessary. The armies had broken out of Normandy. The hedgerow fighting was over. The hastily welded field expedients had done their job. Many tankers never bothered removing them, keeping the devices as good luck charms or potential tools for future obstacle clearing. The naming of the device became contentious. Some called them Cullen cutters, after the inventor. Others called them rhino tanks because the prongs resembled rhinoceros horns. Official army documents called them hedgerow cutting devices. The British, who adopted similar devices for their tanks, called them prongs with typical understatement. Cullen himself preferred they have no name attached to him. In later interviews, he emphasized that many soldiers contributed to developing and improving the device. He particularly credited the welders and fabricators who manufactured thousands of units under combat conditions. "I had an idea," he said in 1965, "but a lot of other guys made it work. They deserve the credit." The unsung heroes. The story of the hedgerow cutter would be incomplete without acknowledging the hundreds of maintenance soldiers who made mass production possible. These men, serving in division and corps maintenance companies, worked around the clock for 2 weeks to equip thousands of tanks. The work was brutal. Welding in August heat while wearing protective gear was exhausting. The steel was heavy, awkward, dangerous to handle. Cutting torches and welding equipment are hazardous in optimal conditions, and these were far from optimal. Yet the fabrication teams maintained production rates that would have impressed factory managers. Staff Sergeant Robert McCormick, serving in the 2nd Armored Division Maintenance Company, kept a diary that survived. His entry from August 7, 1944 reads, "16th day straight working. We've modified 83 tanks so far. The welders are sleeping in shifts. We run out of welding rod twice a day. Guys are getting burned, cut, exhausted. Nobody complains. We know every device we install saves American lives. That's all that matters." The diversity of the workforce deserves mention. The fabrication teams included African American soldiers from segregated units who welcomed the chance to contribute directly to combat operations. They included older soldiers considered too old for frontline combat, but whose welding skills proved invaluable. They included recent replacements who arrived in Normandy to find themselves working in what was essentially a field factory. Women also contributed, though their role was often overlooked. The Women's Army Corps members, serving in ordnance units, handled logistics, procurement, and quality control documentation. While they didn't weld the devices themselves due to policy restrictions, they ensured materials reached fabrication sites and tracked production statistics. The medical impact of the hedgerow cutters was documented by Captain David Thompson, a battalion surgeon with the 67th Armored Regiment. Thompson kept detailed records of tank crew casualties. In the 2 weeks before hedgerow cutters were installed, his battalion suffered 43 crew casualties from knocked-out tanks in hedgerow fighting, of which 19 were fatal. In the 2 weeks after installation, they suffered 11 casualties, 4 fatal. The difference was stark and statistically significant. Thompson's report noted, "The primary difference appears to be that tanks with hedgerow devices rarely present vulnerable belly armor to enemy fire. Secondary factors include improved crew morale, leading to better situational awareness and faster crossing times, reducing exposure to enemy fire. The device should be considered standard equipment for any hedgerow operations." The technical legacy. From an engineering perspective, Cullen's invention demonstrated several principles that would influence post-war military vehicle design. The concept of field-modifiable armor to address specific terrain challenges became standard doctrine. Modern military vehicles include provision for adding specialized equipment depending on mission requirements. The hedgerow cutter also validated the principle of adequate rather than optimal engineering in combat situations. Cullen's device was crude by peacetime standards. The welds were rough, the steel was salvaged, the design was improvised, but it worked well enough when it was needed. This adequacy principle would appear repeatedly in military development. Engineering analysis of surviving hedgerow cutters reveals interesting details about their construction. The welds, while rough, were generally sound. The fabricators understood basic welding principles and applied them correctly, despite field conditions. The steel selection showed practical knowledge. Structural steel, rather than armor plate, was correct for this application. Armor plate would have been too hard to weld and unnecessarily heavy. Load analysis shows the devices experienced forces of approximately 8,000 to 12,000 pounds during hedgerow crossing. The steel prongs, typically 3" by 3" 3-inch angle iron or 4-inch by 4-inch I-beam sections could handle these loads with safety factor of approximately 2 to 3. The weld attachment points, reinforced with gussets, had similar safety factors. The engineering, while improvised, was adequate. Several museums preserve examples of Coulon cutters. The National Museum of World War II in New Orleans has a Sherman tank with original field-welded cutters. The Patton Museum at Fort Knox had examples before its closure. The Imperial War Museum in London has a British tank with similar devices. These artifacts allow modern engineers to study the actual construction. One interesting technical detail that emerged from museum examination: the steel used for prongs often came from multiple sources on a single tank. One prong might be German rail steel, another from a destroyed Panther tank, a third from a beach obstacle, the fourth from a British construction site. The fabricators used whatever steel was available, matching sizes rather than sources. This practical eclecticism worked because structural steel properties are relatively consistent, regardless of origin. The $5 myth. The $5 fix description is somewhat misleading, though it captures the essential truth. Cullen's original prototype probably did cost approximately $5 in welding rod and cutting torch fuel, assuming labor was free, but the actual program to equip 3,000 tanks cost considerably more. Army records from the Normandy period are incomplete, but available documents suggest the total material cost was approximately $60,000. This covered salvaged steel that had to be transported to fabrication sites, welding supplies, cutting torch fuel, and miscellaneous materials. Labor was already paid, Army salaries so wasn't counted as program cost. $60,000 for 3,000 tanks equals $20 per tank, not $5. But compared to normal military procurement costs, this was essentially free. A factory-produced hedgerow cutting device, designed and manufactured properly, would have cost approximately $200 to $300 per tank, including engineering, testing, and manufacturing costs. The total program cost would have exceeded $600,000. Moreover, the factory approach would have taken months. Design and testing alone required 6 to 8 weeks. Manufacturing setup required another month. Production at scale required specialized tooling. The devices wouldn't have been available until October or November, far too late for Operation Cobra. The true savings wasn't monetary but temporal. Cullen's approach allowed deployment in weeks rather than months. This time saving was priceless. Every day the hedgerow fighting continued cost American lives and delayed the liberation of France. Accelerating the Normandy breakout by even 1 week potentially saved thousands of casualties. The monetary comparison also ignores opportunity costs. If American forces had remained stalled in hedgerows through August and September, the Germans would have had time to reinforce defenses, organize counterattacks, and potentially even negotiate a stalemate on the Western Front. The strategic cost of delay was incalculable. The human element. Curtis Coulon returned to Cranford, New Jersey after the war and resumed his career as a cab driver. He married, raised a family, and lived quietly. He rarely discussed his wartime service and never sought publicity for his invention. Friends and neighbors often didn't know about his contribution. In 1964, a historian researching the Normandy campaign contacted Coulon for an interview. The historian had found references to Coulon cutters in after-action reports and wanted to learn more. Coulon initially declined, but eventually agreed to a brief interview. The interview transcript reveals a man uncomfortable with recognition. When asked if he felt proud of his invention, Coulon responded, "I did what needed doing. Lots of other guys had ideas too. Mine just happened to work out. I was lucky, that's all. The real heroes are the guys who didn't come home." This modesty was characteristic. Coulon never wrote a memoir. He declined invitations to speak at military events. When the Army tried to present him with an additional medal in the 1960s, he declined, saying the recognition should go to the maintenance soldiers who built the devices. Coulon's family later revealed that he suffered from what we now recognize as post-traumatic stress disorder. He had nightmares about burning tanks. He experienced survivor's guilt, feeling he should have done more to save fellow soldiers. The hedgerow device, rather than being a source of pride, was complicated for him emotionally. It reminded him of friends who died before the device was developed. He died in 1985 at age 70, having lived a modest life. His obituary in the local newspaper mentioned his wartime service, but not the hedgerow cutter. Only a small paragraph at the end noted he had contributed to tank modifications in Normandy. The broader impact. The hedgerow cutter story illustrates broader truths about innovation in crisis. First, effective solutions often come from unexpected sources. Cullen wasn't an engineer or tank designer. He was a mechanic, a cab driver, someone who understood practical problem solving from years of keeping temperamental vehicles running. Second, institutional resistance to innovation is often the biggest obstacle. The Army's procurement and testing systems, designed to ensure quality and safety, were too slow for wartime needs. Bradley's decision to bypass these systems was controversial but necessary. Peacetime procedures don't always work in wartime conditions. Third, simple solutions are often superior to complex ones. The hedgerow cutter had no moving parts, required no special maintenance, and couldn't malfunction. Contrast this with some proposed solutions, like hydraulic rams or explosive charges, which would have been complex, expensive, and unreliable. Fourth, mass implementation matters more than perfect design. The hastily welded hedgerow cutters weren't optimal by engineering standards, but 3,000 adequate devices deployed in 2 weeks accomplished more than 300 perfect devices would have achieved in 6 months. Fifth, the human cost of technological inadequacy is real and immediate. In peacetime, we can debate optimal solutions and conduct lengthy testing. In war, delay means death. The hedgerow fighting killed American soldiers who would have lived if the devices had been available sooner. This reality focused minds wonderfully. The hedgerow cutter also demonstrated American strengths in World War II. The U.S. wasn't fighting with technological superiority. German tanks were better armored and armed. German tactics were often more sophisticated. But America could improvise, innovate, and implement solutions faster than any other nation. This flexibility, more than any specific weapon, helped win the war. Conclusion: the mechanic's legacy. Today, Sherman tanks equipped with Cullen cutters appear in museums, parks, and memorials across America and Europe. Most visitors walk past without understanding the significance of the steel prongs welded to the front. They see just another modification to a World War II tank. But to those who understand the story, those prongs represent something profound. They represent the power of individual initiative in bureaucratic systems. They represent the importance of practical problem solving over theoretical perfection. They represent the difference between accepting limitations and finding solutions. Most importantly, they represent lives saved. Every tank equipped with a Cullen cutter was a tank that could cross hedgerows without exposing its crew to unnecessary danger. Over the weeks of hedgerow fighting in August 1944, this meant hundreds, possibly thousands, of American soldiers survived battles they might not have otherwise. The mathematics of survival are impossible to calculate precisely. We can't know which specific soldiers lived because of Cullen's invention. We can't identify the children who were born, the families that stayed intact, the futures that unfolded, because one mechanic had an idea and welded some scrap steel to a tank. But we know the aggregate impact. We know the hedgerow fighting became less lethal after the devices were deployed. We know Operation Cobra succeeded faster and with fewer casualties than predicted. We know the Normandy campaign accelerated dramatically once tanks could cross hedgerows safely. Curtis Cullen's $5 fix, the invention of a cab driver turned tank mechanic, changed the course of the Normandy campaign. It helped break the deadlock that threatened to extend the war into 1945. It saved American lives and accelerated the liberation of France. It demonstrated that sometimes the most important innovations come not from laboratories and engineering departments, but from soldiers in the field who refuse to accept that problems are unsolvable. The legacy extends beyond World War II. Modern military doctrine emphasizes the importance of field-expedient solutions and rapid prototyping. The U.S. military's current innovation programs specifically encourage soldiers to identify problems and develop solutions without waiting for official channels. This approach traces directly to lessons learned from innovations like Cullen's hedgerow cutter. In an era when military technology often costs billions of dollars and takes decades to develop, the story of the $5 fix that saved thousands of tanks reminds us that innovation doesn't always require massive budgets or advanced degrees. Sometimes it requires only observation, creativity, and willingness to try something new. Curtis Cullen saw a problem, conceived a solution, built a prototype, and proved it worked. The entire process took days. The cost was negligible. The impact was incalculable. That's the power of individual innovation when it meets institutional flexibility and urgent necessity. The steel prongs welded to those Sherman tanks weren't just metal, they were determination made manifest. They were American pragmatism in its purest form. They were proof that sometimes the best solution to a complex problem is the simplest one, and sometimes the right person to solve that problem isn't the expected expert, but the observant individual who refuses to accept that nothing can be done. Every time we see those modified tanks in museums, we should remember Staff Sergeant Curtis Coolin Jr., the cab driver from New Jersey, who saved thousands of lives with scrap steel and welding equipment. His story reminds us that heroism takes many forms, that innovation can come from anywhere, and that sometimes the most important question isn't what should we do, but simply what can we do with what we have. The $5 fix saved thousands of tanks, accelerated the liberation of Europe, and demonstrated that in crisis, practical innovation beats theoretical perfection. That lesson remains as relevant today as it was on a July afternoon in 1944, when one mechanic looked at a pile of scrap metal and saw salvation.